Good morning. I would like to welcome you to a Regenesis webinar presentation on groundwater and soil remediation. My name is Callum Nash and I will be your host for this morning's event, entitled Regenesis New Technology Briefing, an Introduction to PersulfOx, an all-new Persulfate in-situ chemical technology developed by Regenesis. And this presentation will focus on an overview of its development and application. To present the development and overview section, I would like to introduce Dr. Jeremy Bernsteingle, Managing Director at Regenesis Limited. Dr. Bernsteingle has a background in bioremediation, for which he holds a PhD and has worked for 20 years in the field of contaminated land remediation. And then to cover the application section, I'd like to introduce Gareth Leonard, District Manager for the UK and Scandinavia. Mr. Leonard has worked in remediation for 12 years, first for a specialist remediation contracting company as a project manager, and for the last 6 years as a district manager for Regenesis. Following this, we will hold a question and answer section. We would like to encourage you to ask questions throughout the presentation by submitting them in the question feature located on the webinar interface to the right of your screen. We will be monitoring the questions throughout the webinar and will answer as many as possible at the end. If we do not get to your specific question, we will reply to you directly via email within the next 24 hours. Finally, for optimal efficiency, we recommend that you close all other internet applications. If for any reason your webinar connection or audio slows down or deteriorates over the course of the event, you should simply close and restart your GoToWebinar session. This concludes the introduction. At this point, I'd like to hand over to Dr. Jeremy Bernsteingle to begin the presentation. Jeremy, over to you.
So, thank you, Callum, for the introduction. My name is Dr. Jeremy Bernsteingle, as Callum mentioned, and I'd like to just go through the first stage of this morning's webinar, dealing with the technology itself, part one of this morning's content. So, before I go into the new product, I'd like to take a moment just to recap on what ISCO is. ISCO, of course, is an acronym for In Situ Chemical Oxidation. And this, of course, in this present context, is a remediation tool for the cleanup of contaminated soil and groundwater. The technology, in its wider sense, can be used for the treatment of hydrocarbons, for chlorinated compounds such as the dry cleaning solvents, the PCEs, the TCEs, etc., and for oxygenates, MTBE, TAME, and the daughter products of those. The technology involves the addition of oxidizing agents, chemicals which are going to mix with, contact, and oxidize the contaminant species directly. So we have a direct contact technology in which one set of chemicals, the ISCO agents, are added to the soil or groundwater. They mix with and react with the contaminants, and they destroy them directly or render them into innocuous and more biodegradable daughter products. The technology is really best understood as a mass removal technology. It can be used for low concentrations, it can be used for high concentrations up to NAPL levels. However, its greatest efficiency is very much in the mid-range, in the thousands of ppm type range, the hundreds to thousands of ppm scale. Once you get up to free product and NAPLs, whilst the technology can be used, it's often cheaper to look at physical approaches to reduce the mass rather than the chemical approaches to reduce the mass. And similarly, down at the bottom ends, when you're down in the microgram per litre range or approaching the cleanup targets, it can be more cost efficient and indeed more effective to use biological approaches to get to the very low levels. ISCO can be used across the spectrum, therefore, but its greatest efficiency is in the middle range, with other technologies becoming often the performance and or cost selection of choice at the top end and down at the bottom end. Ideally, of course, ISCO can therefore be used in combination with other technologies when the site requires, as part of the treatment train approach. And a major consideration for the selection of the ISCO agent is whether or not it will be compatible with the infrastructure that might be used for the physical removal, and indeed with follow-on bioremediation. Will it actually inhibit or will it enhance follow-on bioremediation? We'll touch briefly on some of these considerations further on. So, in the field of ISCO, Regenesis have had an offering in this particular area for about 7 years now, since about 2005, based on the principle of surface-mediated oxidation. This employs a patented heterogeneous catalyst technology that forms the principal theatre of activity of the oxidation of the contaminants. The first product that we put out using this was called Regenox. We've now extended the use of the catalyst to a new persulfate-based product by the name of PersulfOx. But before I get onto that, let me speak briefly about the process itself. So what you see in the image on the screen in front of you is a simple geometry optimization calculation, a cartoon, if you like, of the structure of silica, oxygen and hydrogen atoms forming a silicate surface, a silica surface. What you have is an amorphous, heterogeneous catalyst surface that will sorb both contaminants relatively weakly and the oxidants directly, so that the two are brought together in the same space and time to react together. And indeed, some of the intermediate species of the oxidation, the radicals that can be formed by the oxidants through the process, will also bind to different degrees onto the surface. The relevance of this is that the target and the oxidant are brought into the close proximity that is necessary for the reaction. This increases the efficiency of the reaction substantially. It reduces wastage, it reduces reaction of the reagents onto non-target species, and essentially provides what strictly in chemistry would be a catalyst technology. The silica itself is not used up in the process. Once the contaminants are oxidized, there'll be space for more to sorb and oxidants to sorb, and the process will repeat. So the catalyst is not consumed. The destruction that will take place through a variety of forms. There will be direct oxidation between the ISCO agent itself and the contaminant, but there will also be the formation of various radical species. These can be self-propagating, highly reactive intermediates from the oxidation that will massively increase the destructive power of the ISCO agent. Some of these will be free radicals in solution, and some will be bound radicals, which will be associated with the silica surface. The surface that we can see here is the grey silica, the red oxygen, and the white hydrogen atoms. The black structure that you can see is a ring of 6 atoms at the top would be an illustration of a benzene ring, with the principal functions being the aromatic 6 carbons in the ring with the associated hydrogens shown on there. In this case it's sorbed or bonded to, yes, sorbed I think would be the correct form onto the silica.
So to go back to the beginning of our use of surface-mediated oxidation, I'm going to wind the clock back about 5 years, about 7 years in fact, to 2005, when we first started using the surface-mediated oxidation with our initial ISCO product, Regenox. Now, Regenox is based around sodium percarbonate rather than persulfate, and to date it's been very successful. It's been used on well over 5,000 sites around the world. It's effective on hydrocarbons and chlorinated solvents alike, and importantly it has a very high compatibility with underground infrastructure, and indeed leaves the system primed and ready for follow-on bioremediation, both of solvents that may be treated, the chlorinated solvents, but also with hydrocarbons. The sodium percarbonate is effectively a way of holding hydrogen peroxide in a ligand structure to deliver it more reliably into the formation without it reacting on immediate contact. It's typically, Regenox is typically applied at about a 3 to 5% solution. In the picture you can see a Regenox application taking place at the Cape Canaveral Air Force Base down in Florida. Its selection in this particular site for treatment of hydrocarbons was based principally on a combination of the fact that it's effective against hydrocarbons, but more because the whole site is riddled with underground services, as you might imagine at a space station. And it was critically important that the oxidant would not be destroying that infrastructure. So you can look across the literature and it'll become evident that there are a number of reagents that have been used in the environmental field for in situ chemical oxidation. These include ozone gas, O3, permanganates, both sodium and potassium permanganates, hydrogen peroxide, either as it is or activated at low pH and with an ion catalyst as in Fenton's reagent, and persulfates. Now, Regenesis is always looking to expand our toolbox of technologies that we make available to environmental professionals. And we've been looking at persulfates in particular, attracted by their high solubility, their reasonable stability, and the fact that they can be effective against a broad range of contaminants when they're properly activated. For more information on any of these, I don't intend to discuss them at length in this particular seminar. I want to get on to PersulfOx, but I would recommend to any of you who wish to follow this up further to take a look at a book edited by Segrist et al. That came out a couple of years ago on in situ chemical oxidation for groundwater remediation, which speaks directly to our industry and reviews the various ISCO agents that are present. So persulfates have the attraction of reasonable stability, pretty good solubility, up to about 40% at maximum, and a broad reactivity given proper activation. What are they? Well, here again is a cartoon of sodium persulfate. What you can see in the image are the two sulfur molecules shown in yellow, the oxygen around it, and the sodium cation floating off in solution. So the formula is Na2S2O8. The molecule will release about 6.7% of its mass as oxygen that can react with the contaminants. So the active oxygen content is about 6.7% weight by weight. Persulfates are colorless crystalline solids, and they're strong oxidizers. Their standard electrode potential against hydrogen is just over 2 electron volts, which is up there. Persulfates traditionally have been activated through a number of means, the most common of which are chelated metals, for example, iron held in a chelating agent such as EDTA, heat, hydrogen peroxide, and high pH, caustic soda, sodium hydroxide, etc. pH is up above 10, or some references say 11. It's important to activate the persulfates simply because the high stability that it exemplifies in the field can play against the remediation professional. It can just sit there for too long without reacting, and hence the activators kick off the reactions to actually destroy the contaminants. The various activation methods that exist on the market are not created equal. They each have their strengths and weaknesses. Chelated metals are a relatively simple approach, but they're not as effective as some of the other approaches. They're fine against chlorinated ethenes with a double bond. They're fine against BTEX, etc., where again you have an unsaturated hydrocarbon. They struggle more with longer chain hydrocarbons and also with single bond chlorinated solvents. They have their place. There's a note to that end. Heat is very effective as the temperature of the soil and groundwater are increased either through electric heating or through steam injection or whatever it may be. The reactivity and aggressiveness of sodium persulfate increases tremendously and can get rid of a wide range of contaminants. However, this is not without cost. To heat up a large body of soil and groundwater takes time and it takes money. It can be an effective approach if the treatment area is small and concentrated, but as the site gets larger and wider, the practicalities and cost concerns tend to make the approach less practical. Hydrogen peroxide is more effective than chelated metals, less effective than heat, generally speaking. But again, it comes with its own issues. Hydrogen peroxide itself presents health and safety concerns, not only from contact, but also through the very high reactivity that it presents when it hits the groundwater and the soil itself. This can lead to an awful lot of off-gassing, bubbling, back pressures, and vapor intrusions, etc. Base activation, where a caustic material like sodium hydroxide would be added, again can present direct health and safety concerns from the caustic material itself and its handling and mixing on site, but also to be effective in the soil and groundwater for the actual activation. The pH needs to be maintained above about 10. Some references say 11 for certain contaminants. Now, this requires enough of the base to be added to overcome the natural buffering capacity of the aquifer. And beyond that, as the persulfate reaction proceeds, it will typically acidify. Now, in pure solution, the pH will go down to about 2. In an aquifer, depending on the degree of buffering that's intrinsic to the aquifer, it may go down to about 2, or it may be less than that. It may stay around about neutral. It depends very much on the aquifer itself. But either way, the acidic nature of the persulfate as it releases its oxygen is going to need a substantial amount of additional base added to the system to compensate for the drop in pH that the reaction will put forward. So to get the best out of persulfate whilst removing some of the challenges or downsides of some of the activation methods, we've developed the product PersulfOx, which this webinar this morning is to introduce. PersulfOx is a catalyzed sodium persulfate. The persulfate is the same as in other persulfate technologies. Again, it's based around the formula Na2S2O8. But the product makes use of the surface-mediated oxidation developed by Regenesis and that has been used with Regenox for the last 7 years or so. Importantly, this enables it to be presented, sold as an all-in-one product. It does not need anything else added to it other than the water for mixing it up and putting it in the ground. It's shipped to site as a powder. This makes it lightweight because there's no liquid being transported and harder to spill, etc. It's very simple and easy to transport and to handle. What's it made of? About 90% of it is sodium persulfate. About 10% of it is the Catalyzed mixture, which is made up of amorphous silica, very fine powder, and the soluble silicates. It has a mild pH in water. The pH, when mixed up for fieldwork, is in the range of 8 to 9. This is just 1 or 2 pH points above neutral. And to put this in perspective, seawater, eggs are something around pH 8. Baking soda is something around pH 9. Some of the benefits of PersulfOx. I think the first thing to say is that the technology is based around a catalyst, and by definition the catalyst is not consumed by the reaction. This immediately adds an efficiency to the reaction. Activators are consumed in the reaction themselves and hence need to be added in a significant quantity, or at least an adequate quantity, so that enough is still present by the end of the reaction for the activator to perform its function. It also requires enough of the material to be brought to site as the activator. Catalysts are different. They are reused and reused and reused as the reaction proceeds. PersulfOx will treat a wide range of contaminants. It will treat all the common classes that we typically encounter within our industry, the chlorinated solvents, the hydrocarbons, the oxygenates like MTBE, ETBE, etc., etc. It is relatively safe and easy to use versus conventional activators. I call it relatively safe because I think it's unrealistic to call any persulfate safe simply because it is such a strong oxidant. But compared to handling large amounts of peroxide, heat, or sodium hydroxide, it is evidently relatively safe. And clearly the field work is substantially simplified, so without having to bring these other reagents to site or handle or store them, it's clear that there are immediate field benefits in terms of use and safety, etc. The material is soluble. The solubility of persulfate does go up to about 40%, but for field use we find the range of 10 to 20% entirely adequate. And of course the rate at which a material will go into solution decreases as you get closer to saturation. And we find about 15% entirely adequate for field usage, and very fast and simple to put into a solution ready to inject. How well can persulfate treat contaminants? Well, here's an extract of one of the technical bulletins that can be found on our website, either www.regenesis.com under the Resources tab, or indeed the website for PersulfOx as a product itself, PersulfOx.com. And here you can see some data from lab studies in which some of the most common classes of contaminants that we encounter in our industry are dealt with, some representative classes. What you can see here are BTEX, TCE, 1,4-dioxane, which is often used as a stabilizer for PCE and TCE, and dichloroethane, chlorinated alkanes, shown here. In each of these tests, the starting concentrations were about 200, thereabouts, 100 to 200 milligrams per litre. And the systems were set up in triplicate, both the controls and the test systems. The control systems did not have persulfate added, they simply had water added in similar quantity. The PersulfOx systems had PersulfOx added, and the data that you can see are the concentrations after 7 days of reaction. On the far right column is shown the degree of oxidation, not compared to the starting concentration, but the degree of oxidation compared to the control. And the data are really showing a range of oxidation that goes from about 88% up to 99% or more. So we've got 1 to 2 orders of magnitude contaminant reduction across each of these classes over about a week. And as I say, the data are averages of triplicate samples, both of the test systems and the control systems. So to summarize some of the key benefits of the two ISCO products that Regenesis presently offers. Regenox, the earlier offering based on sodium percarbonate, which of course is still available, has a very high compatibility with bioremediation. You might expect it to, given that Regenesis has worked so widely in the field of bioremediation and enhanced bioremediation. Both hydrocarbons and chlorinated solvents can be treated with bioremediation to get to very low levels of contamination after ISCO with Regenox. Regenox also has a high compatibility with infrastructure, metallic, concretes, whatever it may be. Persulfates and PersulfOx has a compatibility with bio, but really just for hydrocarbons. It would not be the product to reach for chlorinated solvents if it's anticipated that chlorinated solvent bioremediation will be needed as a follow-on technology. This is in common with any persulfate approach, where after the reaction has proceeded, the groundwater will have high sulfate concentrations within it, which will compete with the chlorinated solvents for any electron donor that has been put in the groundwater. So PersulfOx should not be the technology to reach for as a front end to a chlorinated solvent biotreatment project. PersulfOx has a higher solubility than Regenox in solution. It can be added in a higher concentration, which has benefits on some sites. And for field use, it also carries some of the benefits of being an all-in-one formula, simplifying field work substantially. When it comes to the selection of oxidants, it can be quite a complicated business, as it will depend on the contaminants, the timescales, the site, the formation, the project, the infrastructure, the geochemistry, and a range of different parameters. And for this reason, Regenesis is very happy to offer evaluations and recommendations free of charge based on theory and based on growing back catalogue of experience. Regenox is recommended for very many sites. It is a very easy reach for tool for chemical oxidation because of its simplicity and safety to use, and because of its compatibility with bioremediation infrastructure, equipment, and the fact that it can be used across the range of most contaminants that we might encounter. PersulfOx tends to be reached for sites where, for one reason or another, there are benefits of putting in a higher concentration of ISCO solution. For example, limited permeability formations. The higher concentration that it can go in with can enhance its penetration of the immobile porosity through its diffusive spread into the subsurface. And indeed, some customers simply prefer Persulfate for whatever reason, and if Persulfate is the oxidant of choice, then PersulfOx provides benefits of improved ease of use, handling, and safety. So to summarize this section, PersulfOx, the new chemical oxidant from Regenesis based on Persulfate, is an all-in-one catalyzed material. It uses the surface-mediated oxidation that is patented by Regenesis and has been used since about 2005. It can treat a wide range of contaminants, the floaters, the sinkers, the oxygenates, the single bonds, the double bonds, etc. And it's locally warehoused from a number of different warehouses within Europe and can be obtained and taken to site very simply and quickly. It's safe and easy to use. I've mentioned it in passing. Gareth will mention it much more in the following section, which deals much more with the practicalities of use in the field. So with that point, I'll hand over to Gareth Leonard, and would also encourage you to type in any questions you might have with regard to the section you've just heard, or indeed to Gareth's section, which is to come now. Thank you very much.
Hello everyone, my name is Gareth Leonard. I am the District Manager for Regenesis for the UK and Scandinavia. As Jeremy mentioned, I'm going to be talking to you today about some of the practicalities of using PersulfOx, how it's supplied and how to use it on the site. So just an outline of what I'll be going through, the application methods, what the product looks like and the packaging, equipment to use, PPE to be wearing, mixing equipment on the site, monitoring during the mixing and monitoring during the injection work, a few do's and don'ts, and then I'll walk you through what we've just talked about on a real site, and then give you some example results at the end. So application methods, PersulfOx can be injected via direct push injection. For those of you who've not seen this before, the picture on the right there is a direct push injection rig. It's a bit like a window sampler, but generally a bit more powerful. What it can do is drive in hollow stem rods down to the depth that you want to treat. It has spring-loaded injection ports at the end. These open when you pump. You apply the amount of product you need. You pull back, you apply the amount of product you need, so that you get the right dose in at the right depth. It can also be applied into wells. It's often applied into wells because it can be more economical to use wells, because when you're using in situ chemical oxidation, you're usually looking at multiple applications. So if you've got the one mobilization to put in the wells, and then you're just coming back with a van and clipping onto those wells, it can often work out that it's a little bit cheaper than direct push injection. On this picture here, they're using a downwell packer to inject into the ground. It might be that you just connect to the wellhead using PersulfOx. It can be placed into excavations. Once you've done an excavation and you might have done some skimming or pump and treat, you can place PersulfOx into the excavation. You can also mix PersulfOx into soils to treat the soils. It's perfectly viable to do this, and also using Regenox. Technically it works very well. It can get out of kilter economically because of the demand in the soils, but it's certainly something to consider, but a pilot test would always be recommended. Today we're going to focus on wells and direct push injection, because that's generally how it is used. So PersulfOx is a single part product, as Jeremy mentioned. The catalyst is already mixed into the product. Now Jeremy went through how that works. What it means in reality is that it makes the product very simple to use. Basically all you're doing is placing PersulfOx into water, mixing it up until it dissolves, and then it's ready to go. You can just pump it into your application points, whether it's direct push or through wells. This means that you don't need to apply a lot of activator with the product. Activator could be caustic, it could be hydrogen peroxide. Caustic has a very high pH. Hydrogen peroxide is a very aggressive oxidant. So not having large volumes on these sites is a benefit. It makes it much safer to use for the guys on the site in having it stored there and handling it on site and also mixing. This has a knock-on effect that it saves on costs as well. The activators aren't free. You will have to purchase the caustic and hydrogen peroxide, so not needing them will save you money. It gives you a reduced preparation time because the catalyst is already mixed in. You're simply mixing this product with the water. There's not an extra step involved in putting the activator in there. It also means there's a dramatically reduced application volume because you're not needing the large volumes of activator, which means mixing and injection, the program length is reduced, so you get a reduced injection time. So there's a lot of savings to be made there on the site. PersulfOx packaging, there's two options. For those of you who've used our products before, you'll recognize this style of tub. For a small site, we would provide the product in these tubs. They're a plastic tub. You open it up, there's a plastic bag inside with 13.6 kilograms of the product in there, ready to mix up. For larger sites, we would provide ton pallets with 40 25 kilogram sacks on there. You can just see a string on the top right there. You just basically separate that string, pull it across, the sack opens, and it's ready to go. The sacks do have a plastic lining within them, and the pallet will be plastic lined as well, but you could only really consider it to be shower proof, so bringing it to site you will have to store it in a container or under cover. So equipment, looking at the pumps that you have to put in the ground, you put the product in the ground, generally you're going to be looking at wanting a pump that can pump quickly to reduce your program length. You're not going to need a pump that needs to be able to pump in at a particularly high pressure. You just want to get it in at a rate that will get the product into the mobile porosity so that you'll mix with the majority of the contamination and break that down. So a fairly cheap diaphragm pump is ideal for a site like this. This is an air-driven diaphragm pump made of plastic. You can get stainless steel ones as well for this use. Yamada and Wielden, there's lots of makes of them. Slightly more expensive is a positive displacement pump or a multi-diaphragm pump. Behind that faceplate there are 3 diaphragms, and there's a rotating plate at an angle behind that spins round and basically compresses each diaphragm so that you get a smoother flow. With a diaphragm pump, the one on the left, the Wielden pump, it's air driven. You'll basically get a surge of product and then nothing and then a surge of product. With the positive displacement, you get a much smoother flow. They both pump very quickly. The positive displacement pump can give you a lot more pressure if you need it for that particular site. Other pumps you could use are progressive cavity pumps, such as a Moino, specialized piston pumps, such as a Roop. These would have to be stainless steel or at least have very good seals in them. Likelihood is they're going to be too expensive for what you need. So generally on these sites, you'll be looking at a diaphragm pump or maybe a positive displacement pump. Other important equipment, you need a pressure gauge to check the pressure that you're putting it in at, and we'll come on to that in a little bit more detail in a couple of slides. You need flow meters to see what rate you're injecting at, but also totalizers to see how much goes into each well. If you're doing injection into multiple wells, you need to, don't assume that it's going evenly into each well. You need to measure how much is going in so the calculated dose gets placed in the right place. The equipment should be chemically resistant. PersulfOx, sulfate chemical oxidation, it will react with metals, so you want to avoid that in your mixing system, and I'll come on to that in the next slide. So make sure you wash and flush the equipment regularly, keep it clean, don't allow it to build up with silt or dirt. So for the equipment you need to use chemically resistant materials, so in your pipes and tanks use stainless steel. 304 and 316 are just the commonly used stainless steels that you'll find. PVC for your tanks and your wells, HDPE for your pipe work and your tanks as well is all absolutely fine. Hoses, you want a fiber reinforced plastic. These are fairly cheap hoses, but they won't react with the product at all. And seals, we've got Kynar, EDPM, Viton, Teflon. Essentially what we're saying here is don't use cheap seals. Cheap seals will basically be broken down by the product. You won't save money because you'll have to keep stopping and replacing these seals. So get a good seal that's chemically resistant and it'll last you through the project. You want to avoid things that will react with the PersulfOx. This would be mild steel, galvanized steel, copper brass connections. You might have hose tails in there. You might have them as a T-piece in a manifold. Make sure you're not using any of these. And natural rubbers in your seals, these will become brittle over time and start to leak, so you'll have to keep replacing them. Okay. PPE, because you're not using a lot of caustic or hydrogen peroxide, you can use fairly standard PPE for the site. The product is an irritant, so you don't want to get it on your skin. So when you're mixing, make sure you've got long-sleeved overalls on. Make sure you're covering your skin up. Use gloves. Nitrile waterproof gloves would be the best because obviously you're making up a liquid and you'll be getting splashes on yourself. Goggles to protect your eyes from splashes, or you can use safety glasses as long as they've got sidebars protecting you. Obviously the high vis and the helmet and the boots that you would expect to wear on a site anyway. You'll need a dust mask to avoid breathing in the dust. A typical P2, an EN149 mask, so just a standard dust mask, is absolutely fine. If you have got a large site and you've got a worker whose job it is to do the mixing and they're going to be there all day, every day, you might want to have them wearing gauntlets. You might want to have them wearing an apron because they're going to be much more exposed to the mixing. They'll be leaning over the tank and they could get essentially a wet chest from the end of the tank, and it could get a rash from that, so just protect them a little bit more. But really it's just standard PPE for the site. This slide just shows how to add the PersulfOx into the water and minimize the dust that's being produced. So you've got the tank on the left there, you've got the water in there, you've taken the sack out of the tub, opened it up, just holding the top, place the open end of the sack into the water, underneath the surface of the water, and pour it in so the product goes into the mix under the water. Remove the sack and dispose of it. You can then mix up the PersulfOx into the water and you won't have produced any dust. It just reduces the amount of dust in the air. When mixing, use chemically resistant components, so use PVC or HDPE tank. Try and use stainless steel for your paddle mixers. If you're not using a stainless steel paddle mixer, use it briefly and pull it out and make sure it's clean. Make sure your tanks and equipment are kept clean. Don't let silts build up in there or dirt build up in there. That's mainly from the point of view is you don't want that building up and then going through the pump in one big slug. So after every batch you've done, just make sure that as the last bit of the batch is going into the pump, flush it out with a little bit of water behind and pump that through. So mix it up and continue to agitate. I'm saying it this way because the chances are you're not going to use a stainless steel paddle mixer, so get the mix done initially using your standard paddle mixer, pull that out, wash it, and then get your high volume transfer pump, something like a centrifugal pump, stainless steel, or with decent seals. Keep moving that mixture around until the product's entirely dissolved into the water. So the in-tank mixer might be a plasterer's paddle. The other thing you can use is a bubble bar, just to keep the product moving over. You just use a plastic pipe into the bottom of the tank with a holes along it, connect that to a compressor and bubble air through, and that'll just keep the tank turning over. So dilution, recommended application solution. As Jeremy mentioned, we suggest a 10 to 20% mix weight for weight, that's PersulfOx, into the water. The idea is that you want to get as much contact with the contamination as possible. So you want to get in the largest volume you can so that you maximize that contact between the chemical oxidant and the contamination to break it down. Now, the formation may not want you to do that, basically. So let's have a look. If we had 100 kilograms of PersulfOx that we wanted to get into the ground, if it's a highly permeable formation, you might go for a 10% mix, which would mean into that well you're putting 1,000 liters of the mixture. Now, that might be what we designed, and you come to site and try that, and the formation isn't as permeable as we'd hoped. You can then reduce that dilution, so 15% would be 670 litres, and 20% is 500 litres, so half the 10% mix. So what you'll find when you're using the product is that you'll have to dial into what the formation can actually accept on your first day, and from that point on you can move through the site confident of the correct dilution that you want to use. So mixing, as we mentioned, it's a single step product, so you just mix it into the water. The mixing time is very rapid. It only takes a few minutes of mixing it through. On a summer's day, should we say, 15 degrees C. Even in the winter, let's say 4 or 5 degrees, it will still dissolve into the water. It'll just take a little bit longer. What you might want to do is, while you're mixing it with your paddle mixer, also have your transfer pump recirculating in the tank as well. It'll just help bring the temperature up by a couple of degrees, which will just keep you ticking along a little bit quicker. So application monitoring. Once you've dissolved the product into the water, you'll get a pH of about 8 to 9. It'll stay very stable. If you find that it's dropping, it's because you've got some metal in your system somewhere, and what's happening is you're getting a bit of sulfuric acid produced, and it's dropping that pH. So if that's happening, just make sure you put that batch into the ground, then wash down the system and have a look at your seals, have a look at your connections. There might be a brass hose tail or a galv hose tail that you didn't realize you had in there, and just swap that out before you do the next batch, basically. Monitor the physical delivery. You want to inject it as quickly as possible, but you don't want to build the pressure too much, and I'll come on to that in the next slide. So monitor the rate that it's going in, monitor the pressure that you're using, and monitor the volume that's going in, not just at the tank, but using a totalizer for your wells, so you can tell what's going into which well. So, field application. It's a single-step product, which means it's very straightforward to use. As we mentioned, just put it in the water and mix. It gives you a very moderate pH at the surface where you're mixing. So it's not corrosive on your ground equipment. Below ground, you will be getting the pH dropping. Okay. So if you're using direct push injection, as you pull those rods out, just wash those rods down probably in one of our buckets that's empty. That's what tends to happen, and put it to one side, just to make sure that they don't corrode. This is pretty typical of injecting any material. As the direct push rods come out, just give them a wash. It just makes sure they're clean for the next round, and you don't give yourself any problems. Okay, application rate. It says low. The application, you want to inject it as quick as you can, basically, so that you're not on site forever. Now, it's always a balance, though, as to the rate you can get it in against the pressure that you need to get it in. And what you want to be led by is the pressure in this case. You don't want the pressure to build up, because you want the product to go into the mobile porosity where your contaminant mass is, to break that down. So injected it at a rate where your pressure doesn't build too much, and that'll then control the flow rate going into the ground. Now, that might mean that you're not injecting it at a particularly fast rate. So in order to make your program length sensible, it's best to inject into multiple wells at once. So even if you're getting it at a slow rate, you're getting a decent volume in over time. So you might want to have a manifold, and then that would clip to 3 different points, for instance. Okay, some do's and don'ts. Do use appropriate PPE. As I've said, it's standard site PPE, but do take it seriously. Wear your dust mask, protect your skin and your eyes. Use chemically resistant equipment and components. If you don't go for cheap material, or think that you can get away with using mild steel or galv, it will corrode. You will have to stop. You will have to swap it out. So get the correct equipment. It's not particularly expensive equipment. It's not particularly complicated equipment. Just make sure you've got the right equipment within your mixing and pumping lines. Use appropriately sized pumps, pressure gauges, and flow meters. If you're injecting at a low pressure, make sure that your pressure gauges aren't set from 0 to 100 bar. You know, you're not going to see it going in at that point. You want 0 to 3 bar, 0 to 5 bar, something like that, so you can actually measure it. Monitor the solution during the application. That's the pH, just to make sure that you haven't got any issues within your mixing equipment. Monitor the injection volume, pressure and flow rate during the application, so you're controlling what's going where and at what rate. And use multiple injection points to ensure that you're maximizing the treatment while minimizing the time on site. Don't use non-compatible components, as I mentioned. It will come back to bite you and slow you down. And don't apply under too much pressure. If you do find that the pressure's built up, the concern is that you get fracturing and the product will head into areas that you don't need it. If you see fracturing, what you'll see is you won't get much of a flow rate, the pressure will build up, and then suddenly it will drop and your flow rate will increase. So what you've done is you created a fracture and then you're propagating that fracture. Now, you can at that point stop and try again, or just finish the batch and come back to the well. On the next round, that fracture will have closed out. When people talk about fracking, they're mostly thinking about in the oil fields, the fractures that they create there, they actually pump beads down to keep those fractures open. In the situation we're talking about in unconsolidated material, once you take that pressure off, let it settle, those fractures will close up. So if you have created some fractures in one round of injection, they aren't going to be there the next time. Just be aware that you're going to have to take it steady on that next round. So here's an example site in the US that I'll just walk you through some of the points that I raised before. It's an old industrial unit. They're looking to redevelop. It's currently a car park, and underneath it is impacted with chlorinated solvents. Groundwater is at 3 meters below ground level, and it's silts and clays with some sand lenses within it. So what they've gone for is a grid pattern of injection wells on about a 2 to 3 meter grid in a herringbone pattern, which means each row is offset, and that just helps to ensure that the radius of influence of each well is interlocking and doesn't leave any patches on the site untreated. So the application rates, they're looking to get 115 kilograms of PersulfOx in per well, diluted at 10%, so that's about 1.15 cube per location that they're putting in. These are the injection well setup. For your injection well, when you're installing an injection well, remember it's for injection, it's not just a borehole that you happen to be using. So when you're putting it in, set the slots to the levels that you want to inject at. That'll have gravel packing. Above that you'll have plain with bentonite behind it, but ensure that you've got about 1 meter to 1.5 meters of a sand cement mix. That just ensures that the well is locked in the ground nice and tight. Now you're aiming at doing a low pressure injection, so it shouldn't be a problem, but let's just make sure that that well's in there in case you do have a pressure spike. You don't want that well starting to loosen and move itself slowly out the ground. They've got well heads here that basically just attach to the top of each well. The white and clear PVC plastic bits I'll come on to a little bit later on, but they basically screw onto the top. You can see they've got cam locks there so they can attach the hoses to each one and inject into them. But I'll come back to the wellhead in a little bit. So they mix up the solution using a PVC tank and a paddle mixer, put in the water, add the PersulfOx, mix it up, it's ready to go. They're using a small air-driven plastic double diaphragm pump. So the product comes down the reinforced plastic fiber hose. There's a 1-inch cam lock there to the top of the diaphragm pump. The diaphragm pump is basically then plugged into a compressor. The compressor will make the diaphragm pump pulse, and it'll pulse the product through. So there's the air-driven diaphragm pump. It'll pulse the product out of the pump, along the hose, and they've gone into a manifold here. So it's a very simple manifold, and PVC glued together. It allows you to go to 3 separate wells. Beyond the manifold, you should then go through your gauges. Okay, so you should go through your pressure gauge, your totalizer and your flow rate, so that you can see what is going into each well. It's not a case of just looking in the tank and saying, yes, it's going down nicely, because if you're injecting into 3 wells, one of those wells might be taking all the product and the other 2 are struggling a little bit. So it allows you to control the rate as you're injecting, or it might let you inject entirely into your greedy well and then shut that well down and then inject into the 2 other wells. It's about ensuring that the dose that we've designed goes into the right place, basically. So back to the wellhead, you can see they've got these clear PVC sections, which is a bit flash, but I do like it. It shows you that you can see when the product is being injected in. You can see the hose coming in, just cam lock to that T-piece on the wellhead, and then that goes down through that clear section, so you can see a pulse of the product going down into the ground. They've got a little section on the top there for sampling or bleeding off pressure, or you could put a pressure gauge. What I'd really like to see on here would be a valve, so that you could isolate that wellhead, and a pressure gauge on there, so that if you did get some pressure build up throughout that injection, what you can do is just isolate that wellhead once you've finished injection, clip off your hose, move on to another point and continue your injection, and what will happen is the localized pressure around this injection point will just dissipate over a few minutes. But it means you're not stuck to the well waiting for that pressure to dissipate. You can move on, and it just keeps you much more efficient on the site. Oops. Right, another example site is in New York, just to show some results. What they've got is a mixed plume of petroleum hydrocarbons and chlorinated solvents. It's on a site about 20 meters by 40 meters. The contamination is located in some groundwater within the weathered zone of the top of a sandstone. So the chlorinated solvents are trying to sink down through the groundwater, but they're getting to the competent rock beneath the fractured zone, and they're being held up in that fractured zone, in the weathered zone. They're being held up in the fractures. The petroleum hydrocarbons, the fuel, basically is lighter than water, so it wants to float. It's existing in the top of the groundwater column. So basically these 2 contaminants that would normally try and separate are in the same location in this weathered zone. What they've done is they've dug down to the top of the weathered zone, bashed into the rocks, and basically built a sump. They've put some gravel in there. They've put a wide diameter slotted pipe, backfilled, leaving this pipe in, and that allows them to apply the PersulfOx into that weathered zone. And those are the preliminary results, which were supposed to appear at the end, but there they are. You start with fairly high concentrations, and they drop down very rapidly to almost to non-detect. So the preliminary results, but looking very good. So that was an introduction to what the product looks like, how it's mixed on the site, what you should monitor for on the site, and how to apply it. I've shown you a real site in the US and some example results. We'll now go to the conclusion with Jeremy, and then I think we'll take some questions.
Thank you very much, Gareth. I'll keep the conclusions questions very short, as we're pretty much on the hour now and would like to finish in a timely manner. Simply to wrap up this morning's talks, to summarize, I'd simply state that Regenesis now offers 2 in-situ chemical oxidation products, Regenox and PersulfOx. Both of them employ the catalytic surface-mediated oxidation technology that we have patented. Regenox is based around sodium percarbonate, and thus hydrogen peroxide held in a ligand structure as its principal oxidant, and PersulfOx is based around persulfate. Each of them have their place within the remediation toolkit, and one will be more suitable for one type of site and one for another type of site based on a range of parameters. PersulfOx, the principal subject of this morning's webinar, is a persulfate-based technology. As I said, it's based on the catalytic surface-mediated oxidation around the silica and silicates that are within the catalyst. These are mixed into the reagent as a single component, all in one, product to make for greater ease of use on site and through use of the catalysis rather than activation, a much safer product for field use, field simplicity, and field health and safety, not least because the volume that will be injected of oxidant can be so much smaller because it's not a great deal of the volume isn't taken up by activator. It remains a complex field, and to support our clients and remediation professionals in the use and selection of these products, or indeed other product offerings that we have, our technical services group is available to answer any questions. This can be, the group can be accessed through our website, regenesis.com, and the group is principally involved in providing free application designs, cost estimates and technical assistance through all stages of a project, from initial feasibility assessment through to data review, through to analytical recommendations for monitoring, etc., etc. So we'll now move on to questions, and rather than interrupt this morning's webinar for a pause, I'm going to move straight forward with a few questions that had come in while Gareth was talking, and through the same period of time Gareth is going to prepare a few answers to some of the other questions that have come in as well that would suit him a little bit more. So in no particular order, what have we got? One of the questions that we have is, on a like-for-like basis for petroleum hydrocarbons, would PersulfOx treatment be cheaper than Regenox? The answer, I'm afraid to say, is it depends. It depends very much on the site setting, the matrix, the geology, the concentrations, the site infrastructure, etc., etc. Purely in terms of the oxidants themselves and the degree of oxidizing power that they deliver per unit cost, the two products are pretty much on a par. Whether the use of one product would lead to a cheaper project than another will depend on the site settings. So I'm afraid there's no simple, this one is cheaper for hydrocarbons answer for that. It really will depend on the setting. And again, I would refer the questioner to our technical services group to elucidate any further on that. Another question that we've got that's come in is, how do we know the contaminants are destroyed and not just sorbed to the silica? That's a good question, and it can be answered in two ways. The first is simply that the silicas and silicates do not have a sorptive capacity that can account for 1 to 2 orders of magnitude contaminant loss from the hundreds of ppm level. It simply doesn't work like that. But to add something a little bit more objective to that observation, when we've looked at the degradation of contaminants in the feasibility studies, the product development and the lab studies, then we've taken great pains to look for some of the degradation intermediates that are there. And before I answer that, I'm going to cite a second question which I want to pick up in the same scoop here. What byproducts can be formed during the oxidation process? For example, during the remediation of BTEX or PAH with ISCO, and how can these intermediates be detected in an acceptable range with HPLC and GC? Well, sort of to answer both those questions together, and taking BTEX as a contaminant class, typically a range of degradation or oxidation intermediates would occur. Most of these are ephemeral and transient, but they include, for example, a variety of phenols and oxalates. These are both what you would expect and what you would observe through the various oxidation stages of the aromatics, which is how we know we're getting oxidation rather than just sorption to the silica. Can they be reliably detected in an acceptable range with HPLC and GC? The answer is no, they can't. They tend to be short-lived and ephemeral because what is first formed by the oxidation then gets oxidized itself. And so what we're really looking at is a range of compounds that are formed and then oxidized and then formed and then oxidized. But the fact that they occur at all certainly gives us an indication that we are getting the oxidation that theoretically we would expect to be possible. Gareth, do you want to pick up a couple of questions?
Sure. There's one question here about chalk. Can the product be used in chalk? The answer is no, essentially. If you've got a calcareous formation, such as limestone or chalk, because PersulfOx will create acidic conditions once it's in the subsurface, it's not for chalk or limestone. Basically, you're going to have it reacting with the formation itself. In those situations, you want to be using Regenox, which has got a high pH and won't affect those at all. So that would be the way forwards. Oh yeah, is the product provided in anything else beyond the 25 kilogram sacks? For your larger sites, we can definitely provide the product in dumpy sacks, either the half-ton or 1 ton product. That's not a problem at all. Got any others coming in? Yep, okay.
We're pretty much on the hour, so before the 12 o'clock or 1 o'clock time signal, depending on where you're listening, there are 3 short questions that I'd like to bring forward now. Longevity. How long does PersulfOx last in the subsurface after injection? Typically weeks to about a month is the answer to that. So not so long that it's not really reacting significantly, and not so fast that it's going off before it's really been delivered deep into the formation or that creates any adverse reaction. So weeks to a month is the principal range of activity. A couple of questions specific to contaminants. Can PersulfOx be used against MTBE? Yes, indeed it can, and in fact I touched on this during the presentation. I'd refer the questioner to the technical bulletin number 2 on the PersulfOx and Regenesis website. MTBE is entirely treatable. In the tests that we cited, we got about 99% reduction in 7 days. Field results were also positive, although in practice, depending on the concentration of MTBE that you have on the site, it may be worth considering just straightforward ORC advanced, oxygen release compound advanced, for taking out the MTBE, which we do routinely. PCBs. Is it possible to treat PCBs with PersulfOx? The answer is sadly no. I'm not sure that PCBs can be reliably taken out with many things on the market at all. So PCBs would not be a target contaminant to treat. Do we have any further questions? Gareth, have you got any more on your list?
Just repeat the calcareous one.
Okay, then I think as we're just passing 12 o'clock and more or less on the hour, I will conclude this morning's webinar. There are some questions that we didn't get to. These we will answer either by telephone or by email in the next 48 hours or so. Thank you very much, all of you, for attending our webinar. Very grateful for your attention and for your interest in our products, and we'll be very happy to assist in any further queries that you may have. Gareth's and my coordinations for correspondence there on screen. Thank you very much, and we look forward to joining you on another webinar in the not too distant future.